All right, welcome back. This is going to be midterm 2 for physiology. Dun, dun, dun. I'm making this a huge deal. It really isn't. But so as last time I did this for midterm 1, I want to show you all the problems ahead of time so you can either take a screenshot of it, do whatever you want, print it out, answer them on your own, try to answer on your own, and then I'm going to go over it. So this is going to be question 1. This is also part of question 1. Here's 2. Here's 3. And here's 4. So let's begin. So let's start. So two stimuli are applied to neurons B and C. The stimulus applied to neuron B is 5 times stronger than the one applied to neuron C. Compared to the baseline, what will happen to the transmission of action potentials of the following cells? Circle your choice. So hopefully you realize this is a lateral inhibition problem. If you didn't, well, you should. But let's look at this. So what's happening to cell C? Well, actually, I already told you the answer. It's in the problem. It's two stimuli are applied to neurons B and C. Well, compared to baseline, we're stimulating C. Baseline would be nothing stimulated at all. That's baseline. But since we stimulate C, there's some kind of stimulus. So there's some action potential being generated. So it's going to be higher. What about cell A? Well, cell A has nothing applied to it. So it's going to be no change. Right? Because we had stimulus applying here, and this one's like 5 times stronger. There's nothing here, right? Nothing here. So no change compared to baseline. Cell B, that's also in the answer. But not in the answer. That's in the question. It's higher. I said there was a stimulus 5 times stronger. So we are applying the stimulus. That means more action potentials are going to be fired. Now this is where the lateral inhibition part of the lateral inhibition stuff kicks in. Yeah. Cell D. What's going to happen? Well, the answer is lower. The reason is because A is not being stimulated at all, right? So there's nothing really, no action potentials are going down here. B is being stimulated by a lot. So B is going to inhibit action potential firing of D. So it's going to be lower. What about E? E is going to be higher because we are stimulating B, which means we are going to be firing action potentials in E. But you're probably like, wait a second, what about, cell C? We are getting stuff here, so shouldn't C be inhibiting E? That is true. That is 100% true. However, the stimulus on B is 5 times stronger. So it's going to be making, firing action potentials a lot more on E. So yeah, you would be correct, but there's still going to be a high number of action potentials because of B. All right. Explain your answer to cell D. Mention neurotransmitter answer. So cell D, we said lower. What's happening here is that B is lateral inhibiting D. But how's that actually happening? Well, explain your answer. Okay, so so cell B is inhibiting cell D. How is that happening though? So cell B releases neurotransmitters to cell A telling cell A to stop secreting neurotransmitters to stimulate D, cell D. Okay, let me reread that. Cell B is inhibiting cell D. Cell B releases neurotransmitters to cell A, telling cell A to stop secreting neurotransmitters to stimulate cell D. If this doesn't make sense, let's go over this. So what's happening is that cell B is being stimulated. We already got that, right? And it's lateral inhibiting. What happens is cell B basically goes and tells cell A, hey, shut up. Stop sending more signals to cell D, sorry. It's basically telling, hey, A, stop what you're doing. So cell B releases neurotransmitters to cell A and tells cell A to shut up, stop doing what you're doing, so we don't get any firing to cell B and doesn't get stimulated at all. That's what's happening. You realize you're starting to get poor eyesight. Sorry. You go to the doctor and get a pair of glasses. You put the glasses on, which you feel. About 5 minutes later, you don't feel the glasses on your face, even though you're still wearing them. Why? Draw. I am sorry. Draw the actual potentials you would expect to see in a scenario. So this is a question of tonic and phasic receptors. I mean, a whole video on that. So, what is it? Which receptor is it? Well, this is phasic receptors. Phasic receptors. And it's asking why. So, phasic receptors, they tell our brain information for a short period of time. Okay. And then the graph you would see for this, it's this graph here, and then you're going to get a lot of action potentials here. That's okay, whatever. I don't know why it's slanted. Okay, and then you'd start to level off like that. And then this would be, as time, this is time. It goes on. So you get a lot of action potentials in the beginning because we feel our glasses, but then about 5 minutes later, we're going to start, getting less and less action potentials. That's what's happening. These are phasic receptors. You come across a wizard. He offers you a mysterious potion for the cost of your soul. You accept and take a drink. The wizard notices your heart rate begins to slow. What is a possible mechanism action of this potion? Mention alpha or beta receptors in your answer. Okay, so your heart rate is slowing. And it says mention alpha and beta receptors. So, what's going on? Okay, this is beta receptor antagonist. So what this is normally norepinephrine, I'm going to say norepi, binds to beta 1, increasing heart rate. If blocked, heart rate slows down. Now, if you've noticed, what you just answered is what beta blockers do. If you've ever seen a commercial, about beta blockers, this is exactly what it is. It's a beta receptor antagonist. These are you basically just took a beta blocker. Yay! Okay. What is the entire G protein pathway for the beta 1 receptors? Fun, right? So this is the GS pathway. And it consists of the G protein, which is, activated. Then it is adenyl cyclase. Adenyl cyclase turns on. Which activates CAMP, which activates pKa, which is equals to phosphorylation of proteins. And then we get a cell response. That is the G protein pathway for beta 1 receptors. In the sympathetic system, blank is released from the preganglion neuron and binds to blank receptors on the postganglion neuron. So the answer, for let's say A, the first blank, A, is, oops, okay, it's having a stroke. Okay, acetylcholine. Hello? Okay, whatever, acetylcholine, ACH. And the second blank is nicotinic receptors. Nicotinic receptors. In the sympathetic system, acetylcholine is released from the preganglion neuron and binds to nicotinic receptors on the postganglion neuron. I am sorry, this is bugging me. There. Okay. In the parasympathetic system, the postganglionic neuron releases blank, which binds to blank receptors on the muscle cell. So this, the first blank, is acetylcholine again. In the parasympathetic system, the postganglion neuron releases acetylcholine, yep, which binds to muscarinic. Muscarinic. I cannot spell. Let me redo that. Muscarinic receptors on the muscle cell. Okay. 3. Given the situation, answer the following questions. Question, whatever. We have a drug that, when injected, makes more calcium leave the sarcoplasmic reticulum. Will the amount of cross bridges increase or decrease? Explain. The answer is increase. More calcium means more troponin can push tropomyosin away, exposing more binding sites on actin. Okay. Increase more calcium means more troponin. I'm sorry, okay. I don't know what's going on with the Apple Pencil, but it's like acting up and it's not like drawing nicely. Okay. Actin and myosin interact, but ATP cannot bind to the myosin heads. What is the result? Each situation is independent, by the way. So what's going to happen here is muscles will stay contracted. So ATP causes myosin heads to let go of actin, So no ATP equals no letting go. Okay. Everything is normal, but troponin and tropomyosin are not physically connected together. What happens? I kind of answered this in the first one, but in letter A. But so calcium binds to troponin, but doesn't push tropomyosin away because it's not physically connected. Remember that troponin and tropomyosin are together, they're connected. Troponin, when stimulated by calcium, pushes tropomyosin away. But if they're not actually connected together, troponin can't even push tropomyosin away, so it cannot actually expose binding sites. So binding sites are not exposed, no contraction happens. No contraction. D. We don't get an action potential in the muscle cell in the first place. Explain using the words DHP receptor and ranitidine receptor, or RIRAR. Okay. So this is another way of saying no contraction. But it wants us to use DHP receptor and ranitidine receptor. So no AP means low voltage in muscle cell. So DHP is not stimulated, so it doesn't pull open ranitidine receptors. Calcium 2 plus is not released from sarcoplasmic reticulum, or SR. I just okay. Okay, that works. No contraction, no action potential means the voltage is low in the muscle cell. And DHP responds to voltage. If the voltage is low, DHP doesn't respond. And remember, DHP pulls on ranitidine receptors that's located on the sarcoplasmic reticulum. The sarcoplasmic reticulum holds the calcium that we need for the contraction. Ranitidine receptors block that. So when stimulated, usually DHP would pull on ranitidine receptors, which release calcium. But since DHP is not stimulated, ranitidine receptors are not, cannot move, and so the SR is not opened up. So calcium cannot leave, therefore we don't get a contraction. Last bit of questions. Let's do this. Use the word bank to answer the following questions. Terms can be used more than once or not at all. Don't you hate when they do that? Like the none at all stuff? I hate that. So you have the word bank of horror I created. You got A band, Z line, Titan, H zone, actin, and I band. The sacromere length extends from blank to blank. This is Z line to Z line. Z line to Z line. B. Length of the myosin filament with no actin overlapping. This is the H zone. Come on, don't have a stroke here. Okay, H zone. Length of the actin filament with no myosin overlapping. This is the I band. D. Probably the easiest question on this test. The thin filament. This is actin. It's not a trick question. It's literally actin. Yay! Which is my least. Okay. So this concludes midterm 2. If you did well in this, you'll probably do well in the midterm, in real life. Well, this is real life, but in class, we actually really take this class. If you've struggled on this, here's what I recommend. I was very nice, and each question, I suggest the videos you should watch, my videos. For question 1, I suggest you watch the lateral inhibition video and the tonic and phasic receptors. Watching these 2 videos, you'll know how to answer it. For question 2, I would watch the videos on alpha receptors, beta receptors, and transmission of the reception of the autonomic nervous system. If you watch these 3 videos, you'll be able to answer question 2 completely and get 100%. For question 3, watch the muscle contraction cycle part 1 and muscle contraction cycle part 2. Both of these will help you, so you can answer all the questions. In question 4, just gotta watch the Sacromere regions, where I go over the myosin, H zone, titin, I-band, M line, Z line, all that other crap. Now, here's what I'm going to plan to do. Is I know some people don't have these type of tests. I know some of you have multiple choice tests. So I will make a multiple choice test. It won't be long. It won't be like 50 questions long, but I'll make it, decent length for those people who have multiple choice questions. I'm going to accommodate for everybody here. So that's what I want to do. So until I make the next video, I'll see you guys later. And please like and subscribe. I reached over 100 subscribers, and I am very, very thankful. Thank you so much for that. That really means a lot. If more people watch this, more people will see it, and more people are going to get A's in physiology and other courses I want to teach. So thank you so much. Until next time, later.